Now, Ethernet has been a mainstay of digital communication for decades, but those cables are bulky. They can't be so easily integrated into industrial applications or automotive. So the Ethernet working group has come out with something called single pair Ethernet and requires just 2 wires. We're here to talk to onsemi to find out how their Ethernet controller easily interfaces with simple microcontrollers. So Arndt, lovely to meet you here at the onsemi stand from Embedded World 2022. Obviously, it's been a bit of a pause for the last 2 years because of coronavirus. We haven't seen each other for a while. So what have you been doing in the last 2 years, and what have you brought today to show us?
We're very excited to be here and share the absolute brand new device that we're showing here at the show. What we're showing is a 10-base T1S device, which is a combination of a Mac and a PHY in a single small package. It adheres to the IEEE 802.3 CG, so it's compatible to this, and it's using a SPI protocol defined by the Open Alliance, which is standardized as well. You can download the standard, you can see how that works.
Okay.
And that's enabling single pair Ethernet multi-drop communication, where you have more than one station on a single wire.
So that's an interesting development, isn't it, in the space of Ethernet, because traditionally Ethernet has always had 4 pairs for computers. Right. So tell us a little bit more about the reason we have single pair, just 2-wire Ethernet.
Reason number 1 is the cost, right? You just use 1 pair instead of 2 or 3 or 4. Number 2 is this being a multi-drop system, is you can connect more than one station on a single wire. So you're not limited to point-to-point, you can do point-to-multipoint. The standard talks about 8, we can do way more. We have very low capacitance on the line pins, so we can do up to 40 on a 25-meter segment. Okay. And you don't need hubs or switches or anything, so like if you combine 40 nodes on a single net or a single wire, all you need is 40 ports. On a point-to-point connection, you would need a switch, and you need a port on every end. So to make a connection of 40 devices that way, you would need 80 ports instead of 40. So that's where the saving comes into the game.
And what sort of length is achievable with single pair Ethernet? Because obviously one of the challenges with all Ethernet technology is EMI radiated noise.
Correct. So the standard says 25 meters. We have a demo that we show here that's showing a connection of over 60 meters. We achieved this by using some features that our devices have as a unique standing out feature. We call this enhanced noise immunity. That helps us to cover longer distances at elevated noise levels.
Now, one of the reasons for single pair Ethernet for being developed was for industrial systems. Obviously, industrial communications have been very heavily dependent on field bus. There's lots of different protocols. Do we see single pair Ethernet replacing those, and is industrial one of the key applications for single pair Ethernet?
There is actually the IEEE, when they defined that, they came up with 2 key applications or fields of application. They named industrial first, and they named automotive as well. What you're saying is right. The trend is to basically do away with gateways, and then have a factory build like Ethernet all the way from the cloud down to the field device. That's where our device comes into the game, like small field devices that don't contribute a lot of traffic, so that are okay with a 10 megabit shared medium. That's where they can play. And like I said, you can do away with a lot of ports. You can make this a small, small footprint, low-cost solution. Think of a push button, for instance. You can make that intelligent by adding a tiny little microcontroller that talks to the SPI on our device and sprays the information into the network. That's the basic idea of it.
Now that's an interesting point that you mentioned there about microcontrollers, because obviously when we think about Ethernet, obviously microcontrollers have had Ethernet capability, but typically we're talking about needing a processor with more performance, something like a PC or a powerful multi-core ARM. Yeah. So how can developers get started using microcontrollers and this particular solution?
The sweet thing with this solution is it talks SPI with a predefined protocol, so all that customers would have to do when they want to use this is they have to code this protocol, which is fully documented, into a low-cost MCU solution. All it has to do, it has to be able to service the SPI bus at 15 megahertz or faster. We show on our demo, we show an example of this being our RSL10 device, which is a Bluetooth low energy radio chip that runs a Cortex M3 at 48 megahertz, and still that's able to perform the Ethernet task by running a TCP IP stick on FreeRTOS.
Now also, when an engineer wants to get started, what sort of development hardware do you have available for them to connect this to their preferred microcontroller platform?
Yeah. We have a combination of two boards. The primary platform the customers probably want to use is because it's a little more powerful and it uses Linux and all the features that come with it. Is a combination of two boards. We call this a bridge board that has a certain number. We have the actual eval board. They stick together, and those two together go on the Raspberry Pi. And then we have a tiny little piece of software that acts as a user space driver that integrates basically the traffic into the Linux kernel, so they can get started with that rather quickly. And then we have a handful of example programs that customers can download, one of them being the RSL10 solution using FreeRTOS. We also have a bare metal lightweight IP solution for a third-party microcontroller device.
And one of the challenges with Ethernet generally is obviously trying to control the traffic, and when I'm watching a YouTube video on my PC, it doesn't matter too much if there's a bit of delay over the Ethernet link, so collisions are sort of handled and buffered, but in industrial applications with real-time control, that's obviously not really acceptable. Yeah. What have you been doing to try and handle the challenges of collisions on single-pair Ethernet systems? Right,
this being a multi-drop system, obviously collisions can happen. When you have two drivers talking at the same time, they will actually create a collision. The IEEE has a way of dealing with this, what they call CSMACD. That's a thing developed in the late 70s of the last century, or probably the last millennium. They saw the need for fixing that, and there's an optional feature in the IEEE specification. It's called PLCA, which stands for Physical Layer Collision Avoidance, which runs inside the MAC portion of our device. And the way it works is you have a coordinator that sends a beacon in a more or less regular interval, and that beacon resets the counters on every single device, and then the coordinator is the first one that's allowed to send a packet. Once it has sent a packet, it can only send precisely one. Then the next station is the next station's turn. If a station decides not to send anything, they answer that, which we call the transmit opportunity, with a certain amount of silence. The IEEE says 32 bytes of silence. That makes all of the counters increase as well. So only if your own local counter matches your programmed ID, that's when you're allowed to send. The coordinator keeps track of it. You can tell the coordinator, this is how many stations I have. If it reaches that limit, it basically resets itself by sending a beacon, and that causes all the others to reset. So what that effectively is, it's a round-robin arbitration method, allowing every single device to just only send one packet at a time. It helps because it avoids collision. So you can go with to a much higher utilization of the actually available data bandwidth or link rate. In CSMACD, you start getting problems when you go to 30% or above. This can push it to like almost 100%.
Amazing.
Right? And then we have another feature, especially where you go to extend the range or you're dealing with noise. I mentioned that earlier. This is enhanced noise immunity. That allows you to communicate in very, very noisy environments where pretty much your data eye is about to close. We can still do this. We're using some digital technology to extract that signal anyway. So with that, we can communicate on higher noise levels over longer distance. And we have another optional feature that goes in conjunction with PLCA. You have to imagine when you have a PLCA domain, as it's called, collision. If it's correctly configured, collisions cannot happen.
Okay.
So, but on high noise levels, a device could mistakenly take noise as a collision. And in order to prevent this, we can basically tell the devices to mask the collision detection, so they won't mistakenly take noise as a collision, which increases the data throughput even further. That's basically the two key technologies.
Well, thanks for sharing all those insights about single-pair Ethernet for us. We wish you all the success with this solution. It sounds really exciting and a very interesting application space for Elektor as well, single-pair Ethernet and linking up microcontrollers. All the best with the rest of the show.
Thank you. We're very excited to have this on the show. Thank you for the interview. Thank you.